Welcome to another Great Cow Basic tutorial or demonstration for the PIC16F171 chip family. Hello, my name is Venn. I'm a co-developer of Great Cow Basic and I'm walking you through these tutorials. Let's get into the slides. Today we're going to be looking at using Serial Peripheral Interface or SPI. And we're going to be talking that to a GLCD, a graphical LCD, as a way of representing the communications that you can do with SPI. What am I using? I'm using the Microchip low pin count demo board. I've got a 16F17126 inserted into that, and you can create your own using the breadboard layout as designed by Chris Roper, and that is shown on the right. Let's just talk about SPI for a minute. I'll turn the video off because SPI, or the Serial Peripheral Interface, is a bus that's very often used to communicate data between microcontrollers and other peripherals like this GLCD, shift registers, sensors, and the SD card. The memory SD card is SPI. It uses a clock line, data lines, and you can have two. You can have data out and data in, along with a select line that allows you to choose which SPI device you want to talk to. So you can have multiple SPI devices controlled by one master. You have a shared clock, shared data lines, and then the select line allows you to choose which device to talk to. There is on the internet some confusion across manufacturers about the naming conventions. The typical naming convention on the SPI controller, which is shown in the right top diagram, is SCK for the clock, SDO or serial data out, SDI serial data in, and CS or chip select. Some devices may still talk about, some software may still talk about other depreciated signal names like MOSI, MISO, SS. We're going to have to ignore those because we're going to focus on the normal convention, which is now the chosen option. But even devices may not use these names. You may end up with SDA on GLCD devices, and essentially that is the data input line. And this mapping is always treacherous with SPI. So what we're going to do is connect up a GLCD, and it has 1, 2, 3, 4, 5 connections to control it, plus the ground and VDD. On the left-hand side, there is a listing from the program. We have a data out on A4, SCK on A1. Then there are 3 other lines, which is the DC line or GLCD underscore DC, which is the data or command line. And so what you do, you actually send data or command, and depending on the state of that line, the GLCD knows what to do. We have the chip select, and we have a reset line. This particular one needs a reset line. So we've got it connected up, and some of these ports are PSS, data out, and the clock are PSS controlled. And so that you can move those around quite easily using PPS. So that needs to match. Let me just show you what I've got set up. This is mine on the right hand side. It's no different. It is actually we're going to watch that and see that live. And we're going to look at some lines, circles, and text, etc. And you will notice, for those who are very sharp eyes, this GLCD has an SDA as its input, which is serial data in. And this mapping of SPI is quite inconsistent across the industry. So let's have a look at some code here. Enter GCStudio, and then enter the where you've got the demonstrations. I've got them in my D drive. I also have others. And now I'm inside of the IDE. Yes, I am. Great. Let's open up the Explorer. And the one we're looking at now is demonstration 260 SPI GLCD using the SSD 131. And there's a big old program. So we'll just shut down the Explorer. It's a big program, but let's walk the code. Let's zoom in so we can walk that code. Well, fancy that. We got the same chip, option explicit. And then we got some little changes in here in terms of the our layout, because I've actually put the design into here so that we've got it documented. I've got my STO, data out. I've got my clock. And then down here on port C, I've got my reset line on C.2, my chip select, and my data DC on port C. So that tells me that I need to match this configuration. And we need to do that in the PPS. And using PPS, I've been able to obtain these three values. Let's look at PPS. PPS is now loading, though I can't see it. Hopefully you can. Here it comes. And we're going to select the SDO and the SCK. Those are the two that are controlled by PPS. I have my chip selected, my output. So I need the SCK1. There were, in this particular chip, there are two SPIs, and I'm going to put that. The clock is going to go onto RA1, according to my documentation. And SDO1, which is because again there's two channels. I'm going to put that on RA4 and add that. Now, that's given me some values inside of the cut and paste buffer here, but I've already taken those across because I want to show you how you can control software SPI and hardware SPI. So let's go back to our program. In your mind's eye, I want you to think that I pasted that code in, but what I've done, I'm actually going to run this as hardware SPI, and if it's hardware, I need to use PPS. If it's not the hardware, I need to set my PPS controls to 0, clear them down so that I can use software SPI. And we'll look at that in a moment in terms of its performance. So initially, we're going to run it as hardware, and then we're going to use SPI software. And there's a difference, and that gives you a lot of control on a lot of chips. So, same as yesterday and the previous tutorial, include the GLCD library and tell it that it's a particular type, and this one is an SSD 1331. So I'm going to tell it which ports to use. I've got a GLCD data out, GLCD SCK, the DC, CS, and the reset. And remember, these two are PPS controlled. These are just regular outputs. And the library will handle that for us. There is a define, a comment that says use the hardware SPI or not. In this particular case, we're going to use it. Then the program down here is the same as we saw yesterday. It's exactly the same program as we saw yesterday. And it's actually operating here at the moment. So let's have a look at what it's doing to see what our target is. Here it is. It's chirping away and putting numbers out, etc. It's a very similar program. I use this just to test to make sure it all works. Let's go back to the demo here, and we'll program that up, and we'll bring the lab in at the same time. Here we go. Now, there is some scan rate on this, where you can see the scan rate is causing a bit of a mirror, I forget what the term is, on the display. There's nothing I can do about that. but it's not visible to me. It's only when I'm using the camera. It's now reset. It's blue. Oh, this is a color device, of course. We didn't see color yesterday. And so we can see it flashing away. Let me just turn the lab off. There we go. We can see it on a big camera. Maybe we can't. There we go. It's working now. So if I just go back to the lab there, I'm trying to bring it up in a bigger camera view, but I'm unable to at the moment. It's unfortunate. Back into the IDE. So we can see that there's a run rate on that. It's not a great review, but I'm going to try and deactivate the camera there and then go into the lab so we can see it. There we go. That's much better. So I've deactivated the camera in my IDE. So if I go back into the IDE, I'm just going to turn on software SPI. And it's a function of a library. It's not a function of something I'm doing special here. If I comment that out, I reprogram it. Go back into the lab. We'll see it flash as it reprograms. It's now programming it, and so that the GLCD will stop and reset. And what is interesting is software SPI is clearly slower. In your mind's eye, you can do your own timing. It still operates exactly the same, but there's no PPS involved. And I'll show you again how we did that using conditional. There we go, it's a lot slower. So in the IDE, I took out undefined, that essentially. If I reprogram it, you can see it now here. It's chirping away, 1, 2, and it's much slower when you're using software SPI. Now it's coming back, and straight away you'll see this visibly. It's much faster. There we go. And you can see it's faster. Let's look at the code to make sure we understand how that works. That's quite important. What it's doing, I've modified the init PPS using what's called conditional compilation. If this constant is defined, do this, else do that. And so therefore we can set the PPS within the if def statement, else we set it back to 0. If you don't set it back to 0, you must power cycle the chip. The default values will be retained. If you've got constant voltage on it like I have, you must set these back to 0. Good practice. But what we're seeing is SPI in action. We're seeing SPI doing exactly what it's doing. It's sending data out. It's continually clocking it out. It's raising the CS line or the chip select line. It's sending it commands by raising the data command line, lowering it to send data, and it's doing that at extremely high speed. But Great Car Basic, you can use software SPI or hardware SPI, depending on what your needs are. There's nothing else I want to show you today in terms of what we're looking at. It sort of works, okay? Let's go back to PowerPoint. That's what we've done. We've looked at it quite easily. You saw the commands yesterday in terms of drawing boxes, drawing strings. It's exactly the same command set, so it's no different. And the SSD 1331 library is one of many that you can use for SPI communications, along with a host of other libraries for memory devices, etc., etc. So tomorrow we're going to be looking at 16-bit pulse width modulations to dim the LEDs, and it's an interesting one because there's no library, so we're going to look at how we write directly to registers. And with that, we'll call it a wrap.